Welcome back to our deep dive into Stephen Hawking's A Brief History of Time.
Last time we left off with Einstein's theory of relativity.
Right, and that incredible confirmation of light bending around the sun.
It really changes how you think about gravity, doesn't it?
It does. It's not some mysterious force acting at a distance.
Nope.
But a consequence of warped space-time.
Warped space-time, yeah.
So how does this new understanding of gravity impact our view of the universe on a grander scale?
That's where the story of Edwin Hubble comes in.
Hubble, the guy with the famous space telescope.
The one and only.
I'm guessing he did more than just lend his name to a giant telescope.
He did a lot more. Back in the 1920s, Hubble was observing distant galaxies
Okay.
and noticed something peculiar about their light.
What was that?
It was shifted towards the red end of the spectrum.
Redshift.
Redshift.
That sounds familiar.
It's like the Doppler effect.
Oh, right. Like when an ambulance siren changes pitch as it goes by.
Exactly. Same principle applies to light.
Okay.
When an object is moving away from us, the light waves it emits get stretched out,
Stretched out.
shifting towards the red end of the spectrum. And Hubble observed that the farther away a galaxy was,
Yeah.
the greater its redshift.
So the faster it was moving away from us.
Precisely.
So it's not just that galaxies are moving away from us,
Right.
but that the universe itself is expanding.
The universe is expanding, yeah.
Like a cosmic balloon being inflated.
Good analogy.
Does that mean that everything was once much closer together?
That's the idea. Hubble's observations led to the Big Bang Theory.
The idea that the universe originated from an incredibly hot, dense state billions of years ago
That's it.
and has been expanding ever since.
Ever since.
Redshift makes sense as evidence for the Big Bang,
Mhm.
but was there anything else that supported this radical new theory?
There was.
Yeah.
And it came from a rather unexpected source.
Okay, tell me more.
Two physicists, Arno Penzias and Robert Wilson.
Okay.
They were working on a sensitive microwave detector.
A microwave detector.
Yeah, at Bell Labs.
Okay.
They kept picking up this persistent background noise.
Oh, really?
Yeah, this faint hiss they just couldn't get rid of.
So, like, static on an old radio?
Kinda, yeah.
What did they think it was at first?
I mean, they tried everything to eliminate it,
Like what?
even cleaning pigeon droppings out of their antenna.
So, pigeons almost won a Nobel Prize?
Almost.
Yeah.
But the noise persisted,
Huh.
coming from every direction, day and night.
That's strange.
They eventually realized they weren't just hearing random noise.
What were they hearing then?
The faint afterglow of the Big Bang itself.
Wow, so this cosmic static was leftover radiation from the universe's earliest moments.
It was.
That's amazing.
It's called the cosmic microwave background radiation.
Cosmic microwave background radiation.
And it's considered one of the most important pieces of evidence supporting the Big Bang Theory.
Okay, so we've got redshift showing us the universe is expanding, and this cosmic background radiation as a sort of echo of the Big Bang.
Right.
That's pretty convincing.
It is. It is.
But what does it actually mean for the structure of the universe?
That's where Alexander Friedman comes in.
Okay.
He developed different models of the universe based on Einstein's theory of general relativity.
Okay.
One particularly fascinating model
Yeah.
is that of a finite but unbounded universe.
Hold on. Finite but unbounded. How can something be finite but have no boundaries?
Imagine the surface of a sphere.
Okay.
It has a finite area, but you can travel on it forever without hitting an edge.
Right, you just keep looping around.
Exactly.
So are you saying the universe might be like a three-dimensional version of a sphere?
Precisely.
Okay, my head's spinning a little bit.
It's a mind-bending concept.
It is. It is.
But it fits with the idea of an expanding universe that originated from a single point.
Okay, so if everything was once packed together in this incredibly dense state before the Big Bang, what was there before that?
That's the million-dollar question.
I bet it is.
And according to the Big Bang Theory, the answer is nothing.
Nothing.
Well, not nothing in the sense of empty space,
Okay.
but rather a state of infinite density and temperature,
Intensity.
where our current laws of physics simply break down.
We just hit a wall.
We hit a wall.
We can't even try to describe what caused the Big Bang
Not with our current understanding.
or what might have existed before it.
It's a mystery,
A singularity.
a singularity.
The Big Bang represents both the beginning of our universe
Yeah,
and the edge of our current scientific knowledge.
for now at least.
Okay, so the universe began with this Big Bang,
Right.
and it's been expanding and evolving ever since.
Mm-hmm.
But within this vast universe,
Yes.
we also have these incredibly strange objects
I do.
called black holes.
Black holes, fascinating things.
Regions of space-time where gravity is so intense that nothing, not even light, can escape.
That's right.
And that collapse leads to a singularity as well, right?
It does, yeah, like a mini Big Bang in reverse.
The core of the star collapses into a point of infinite density,
Yeah.
surrounded by an event horizon, the boundary beyond which there's no return.
That's it.
Anything that crosses the event horizon is doomed to be swallowed by the black hole's gravity.
That's the fate, yes.
So black holes are like cosmic vacuum cleaners.
They have that reputation.
Just sucking up anything that gets too close.
Well, they're more than just passive objects.
Okay,
They have a profound impact on their surroundings. They warp space-time.
that makes sense.
Yeah, and influence the motion of stars and gas in their vicinity.
They have to, right? If they warp space-time so dramatically,
Right.
what would it be like to actually witness a star collapsing into a black hole?
Well, it would be quite a spectacle.
I bet it would.
As the star's core collapses,
Okay.
its gravitational pull intensifies,
Okay.
and time itself begins to slow down near the event horizon.
Time slows down.
Time slows down.
Are we talking time travel?
Not quite time travel, but it's a related concept.
Okay.
Because of the intense gravity, light emitted from the collapsing star would be redshifted to longer and longer wavelengths.
Longer wavelengths.
As it struggles to escape,
Okay.
the star would appear to dim
Dim.
and redden
Redden. Okay.
until it eventually fades from view completely
Completely.
as the event horizon forms, leaving behind a region of invisible darkness,
A black hole?
a black hole.
That's both terrifying and fascinating.
It is.
It makes black holes seem even more mysterious and powerful.
They are powerful.
But once a black hole forms, does it just sit there eternally?
Well, that's a question that puzzled physicists for decades.
I bet it did.
And it was Stephen Hawking who provided a groundbreaking answer.
What was that?
He discovered that black holes aren't entirely black after all.
They're not.
Nope, they emit a faint radiation.
Black holes emit something.
They do.
But isn't the whole point of a black hole that nothing can escape?
That's what we thought.
How is that possible?
It's one of those mind-blowing consequences of combining quantum mechanics with general relativity.
Okay, quantum mechanics is back.
It's always there.
So Hawking realized that near the event horizon of a black hole,
Yes.
pairs of virtual particles are constantly popping in and out of existence
Popping in and out, yeah.
due to quantum fluctuations.
That's right.
Wait, virtual particles? Those are those weird quantum things that borrow energy from the vacuum and then disappear, right?
That's them.
Okay,
Normally, these virtual particles annihilate each other almost immediately.
okay,
But near a black hole's event horizon,
yeah.
one particle might get sucked in
Sucked in.
while the other
escapes.
escapes and becomes real.
So it's no longer virtual.
It's real, and it carries away a tiny bit of the black hole's energy.
So black holes actually shrink over time.
That's the revolutionary insight.
They're not eternal after all.
They're not. Hawking radiation means that black holes slowly evaporate.
Evaporate.
But this process takes an incredibly long time.
Okay, so that completely changes my view of black holes.
They're dynamic.
Yeah, they're not just cosmic vacuum cleaners,
Nope.
but dynamic objects that eventually fade away.
It's true.
What happens when a black hole completely evaporates? What's left behind?
That's still a mystery.
Another mystery.
Some physicists believe that information about everything that fell into the black hole might be encoded in the Hawking radiation,
Okay.
while others suggest that the black hole's singularity might be revealed as it evaporates.
A naked singularity.
A naked singularity, yeah.
Didn't Hawking say something about God abhors a naked singularity?
He did. It's called the cosmic censorship conjecture.
Cosmic censorship conjecture.
Yeah, the idea that singularities are always hidden behind event horizons, shielding us from their potentially paradoxical effects.
Okay, so there's still a lot we don't know about black holes.
Absolutely.
Even with Hawking's groundbreaking discoveries.
There's always more to learn.
But speaking of groundbreaking discoveries, black holes aren't the only cosmic mystery that arises when we combine general relativity and quantum mechanics.
Right, to delve deeper into those mysteries,
Yeah.
we need to explore the quantum world itself,
Okay.
where things get really strange.